All right, well, I'm going to go ahead and kick us off. We are joined today by Chad Kitchen with Contech Engineered Solutions. They are a very valuable partners of ours. We do a lot of different products with them. Chad's specifically going to be talking about bridges today. Kelly Shield is our territory sales manager for TV Pipe Solutions and Supply. He's joining Chad today. These guys have been out in the field a lot, meeting with townships, municipalities, going and watching bridge installs. I hear you've got another one next week even, Chad, which is really cool. You guys are going to get to see one that Chad did right here in Idaho, actually. So I'm going to let you kick it off. I do have some questions, Chad. I'll jump in when I think that you're kind of in the right spot to talk about them that have come in already. If anyone on the call has questions, please use the questions box or the chat box. While Chad is going through some of the content for you guys, I'll be monitoring that and I'll jump in and ask those questions in real time. So feel free to use that, raise your hand, message me, whatever. I'm going to kind of just be the moderator of that control panel that you guys see on the right hand side. Thanks for joining us, Kelly and Chad.
Thanks. Yep, of course. All right, ready to get started then, eh?
Yep.
So a quick introduction of myself. I've been with Contech for about, what's it been, 13 years now, I believe. And for most of that time, I've worked in our bridge department. And hence, that's the reason for our presentation today. We're going to obviously talk about cost-effective alternatives to traditional bridges. That's really the intent of what we wanted to share. So I will go ahead and get started with that. So Contech, as a whole, Contech's been around for over 100 years, not necessarily by that name, but over the years we've acquired various companies that consist of what we call our complete bridge portfolio today, and so that's what this slide shows here. We obviously, Contech is a manufacturer producer of corrugated metal pipe, and that's the bread and butter of our company. And we dive into more of the bridge systems, and you can see here, if you follow along the left-hand side of this screen, you see there's two products there called plate and precast, and we call those buried bridges. I'll talk a little bit more about each one of those as we go. Actually, not so much the precast. We're going to focus more on the plate. We're talking about more cost-effective alternatives, and there's a reason why we want to focus on the plate structures at this point. And then below that is our truss bridges, which includes both vehicular and pedestrian steel truss bridges. And then you can see from the chart the various span ranges for each of those bridge types. And a lot of these, in the upper right-hand corner, you see this FHWA box. It's all based on accelerated bridge construction. So these are bridge systems that can be built and assembled in a very short time frame, and usually with very small equipment. Sometimes we'll need a crane, but we'll talk a little bit about that as we go. So again, I mentioned that we'll talk mainly about structural plate bridge applications, and here, as you can see, a variety of applications where this has been used. My favorite is the wildlife crossing there with that moose going through. Very common, very cost-effective use for that type of application. The structural plate come in a variety of shapes and, of course, sizes along with each of those shapes. They really range in cost from least to most costly, starting at the top left-hand side and then moving to the bottom and then moving to the right. So if you can go with a round or even a pipe arch shape, which are two of the most common shapes, these are going to be the more cost-effective styles. And as you can see there, the size ranges. We can get a 50-foot diameter round or a pipe arch, 20-foot span. If you go down a little bit further, there's the arch, the single radius arch, spans upwards of 50 feet there as well. So we can span a pretty good range with these plate structures. And when you compare it to a traditional bridge with the same span, it's going to be probably less than half the cost. to do it this way. So structural plate is manufactured in two different material types, as you can see here, steel and aluminum. There's certainly a reason for this, and it all has to do with durability. There are some conditions, some environmental factors that contribute to durability of a structural plate. And sometimes people get a little bit concerned about using a galvanized steel material in soil because of its the potential for it to rust and corrode. And so being aware of the factors that contribute to that is really important. And so a lot of times we ask for soils report or soils investigation to determine what the pH and resistivity are of the soils and the hardness of the water. And that will help us to determine whether a galvanized steel structure would work and last, say 50 years in those conditions or more. Most DOTs are saying we need it to last 75 years. So it's really imperative to have that information to determine if we can get 75 years out of steel. And if we can't do it with that, then we look at aluminum, which has much higher levels of performance for both pH and resistivity. So that might give us that ability to accommodate a 75-year design life.
So Chad, I think you just answered one of the questions that came in previously, is why you'd pick steel versus aluminum. But the other question we got, is one less expensive than the other based on the material? And I'm assuming that, this is just my assumption, the one that has 75 years longevity is going to be more expensive than 50 years. Is that correct? Based on material?
Yeah, the aluminum plate material is going to be probably 20 to 30% more in terms of cost versus a standard galvanized steel. But when you consider it could last twice as long, you're really getting a really good value for the money that's being spent.
So are these years that you have listed on the slide, the 50 years and the 75 years, are those, that's its design life? I mean, that's kind of its minimum expectancy?
These are specific conditions or situations. If you take the pH levels, the resistivity, hardness levels shown under each of those, that would be the predicted lifespan for each. So if we could plug that in fact, my next slide here is all about durability. There's a website called has service life calculator. It's on the National Corrugated Steel Pipe Association website, ncspa.org. And you can use this calculator to determine, specifically this is built for galvanized steel, it's not for aluminum. But you can take it, the program, and plug in information about, first of all, the desired service life. If you could look at the program here and the boxes, the resistivity and the pH levels, assuming that they are known, or you can make some assumptions. And then an abrasion level, if there is going to be a bottom to the culvert, plug in an abrasion level, and then that will tell you what gauge of material would be required in order to meet at least a 75-year design life.
Gotcha.
So again, those parameters, those environmental conditions change from site to site, and so that previous slide basically just shows you, hey, if this is the condition, you could expect either 50 or 75 years out of either one of those. Any other questions on durability?
Nope, I have more questions, but we're not quite there yet, I don't think.
Okay. Those are great questions. Plate is made up of, well, let me go back up. Steel plate, or galvanized steel plate, is made up of two different corrugation types: a 6x2, 6 inches wide, 2 inches deep, and then a 15-inch wide by 5.5-inch corrugation. And then the aluminum basically has one corrugation profile, and that's a 9 by 2.5. And there are reasons why there are different corrugation types or profiles. And essentially this chart shows us what that is, and I'll refer down to what is about the fourth row there, common span applications, a multi-plate consisting of a 6x2 corrugation really gives us the ability to span up to about 26 feet. If we want to go beyond that, we bump into what we call our bridge core product, which is a 15-inch by 5.5-inch corrugation. It's stiffer, it's stronger, and we can get those spans upward of 60, 65 feet. And so that is the reason for those. There's just more material, more steel to handle the loads and handle the spans with that heavier, deeper profile.
So the 15-inch corrugation would be if you had a heavier load than a 6-inch corrugation, correct?
Yeah, well, they can both handle the same live load.
Okay.
There are limitations on the dead load, the bury depth, how much fill. That's just based on the size of the structure. But generally speaking, a 15 by 5.5-inch has the ability to handle heavier loading, dead load specifically. They're both designed to handle up to HL93, which is the standard live load.
Okay.
And then that's the same with the aluminum plate structure. But again, we're limited because of the one profile up to about 36-foot spans with the aluminum. All right, any other questions there?
Not yet, that answers that one. Okay.
So the nice thing, and this is why we go back to this idea of cost-effective alternatives to traditional bridges. The entire bridge, usually for any plate type structure, is delivered on a single flatbed truck. And so you can see here's one bridge on the truck, and then the other picture is showing that bridge essentially assembled and in place. And that is the entire bridge. So you got one truckload, contains all the materials. Yeah, there's going to be some assembly involved, which is what we're looking at here. Specifically with an aluminum structure, the plates are fairly lightweight and a lot of it can be done by hand, lifting the plates up. I don't necessarily recommend that all the time, but if you got a couple of buff guys out there, I'm sure they could handle that and do it just fine. I was out on a job site, the city of Oakley, and I think I've got pictures of that one where two guys were doing the assembly. And so, and then they did it very much the same as what you're seeing in this picture here, where the bottom left-hand side, the entire shell was assembled and then lifted by a backhoe and dropped into place.
Kelly, you get that question a lot in the field when you're presenting, don't you? How many people it takes to put these type of bridges together?
Yeah, and Chad's right. Oakley they used 2 people basically to assemble that, and then they had the canal company help with their heavy equipment to move it into place to help them just set the bridge into place. And then as far as I know, it looked like when I went out there, 2 guys were finishing it up also. So pretty small
is
crews.
that typical, or is that a very small crew? Like, what would you say an average size crew would be?
Would it be more like 5, Chad?
Yeah, I would recommend at least 4 and probably 5, because usually you work in tandem. There'll be 2 guys, one on the inside pushing bolts through and the other guy on the outside tightening the nuts down. And so if you had 2 of those working on either side of it, and then one guy just running plates and pieces back and forth, I think ideally that's the most efficient.
Yeah, because I see 4 guys in this top left picture.
Yeah.
Okay.
Various foundations, we mentioned these a little bit, full invert, or you can take the invert out and have an open bottom. You can bury that invert. Again, a round structure is by far the most cost effective because you do not need a foundation or a footing. But if it is needed, we can go with a concrete footing, cast in place or precast. That's certainly common ways to do this as well. So I want to show a few case studies and just show some things locally that have been done. This is Lucky Peak Dam near Boise. The Forest Service replaced 3 existing culverts that were essentially perched, and so for any fish that wanted to move upstream, they really didn't have much of a chance to do that. And so the Forest Service came in and they said, hey, we're going to put in a multi-plate to replace those 3 culverts. The multi-plate had an open bottom. It was set on precast concrete footings that had a stem wall. And then you can see the little groove in the top of the stem wall, or that trench, which is what the bottom of the arch would sit in. And so there it is being installed and backfilled with lighter packing equipment. Because these are more of a flexible structure, they do need lightweight but compaction equipment, at least in the first couple of feet around it. So in this case, they went with beveled ends, and instead of using some kind of a head wall and wing walls, they just buried it and then sloped the backfill to match the cut ends, those beveled ends. So that's that one, I think. So this is actually the city of Oakley, and they are assembling an aluminum box culvert, and this is the floor portion of it. Remember right, it was, I have this right, 20-foot 4-inch span, 4-foot 6-inch rise. So fairly wide span and a low profile, which is what these are for. Very similar to what you might get with a concrete box culvert, wide span, low profile. So again, a couple of guys is essentially what they're using to assemble those plates. There's a rib that runs along the top, and that's what you're seeing there, a little profile view of that rib. Those ribs are placed to reinforce the aluminum because it is a softer, lighter weight material. But they act essentially as an I-beam to stiffen it up and give it more structural capacity. And so there it is. Essentially, they assembled it, lifted it. I think you can still see the eye bolts there in the top of the structure, and now they're putting on the aluminum head walls, which is another point. Yeah, go ahead.
That culvert with that width and the rise would not have been available in steel, correct?
No, we don't quite make it the same.
Okay.
Yeah. So that gives you a pretty good view there of, yeah, the span and the height from that profile picture. Here's another project I just want to mention. This is in Park City, Utah, so it's not necessarily local in Idaho there, but I wanted to highlight the use of footings, aluminum footing pads in this case. So whether it is a footing pad or a full invert, it does require a decent soil bearing strength, and that is 4,000 PSF, pounds per square foot. So in this case, they put a fair amount of gravel down to get a good bearing surface, and then they could use those footing pads to place on top. So they're spanning over a stream, which they didn't really have the ability to put in or maybe they didn't want to, especially if there's fish passage, they don't want a full footing, a full invert. So putting on a footing pad is a way to get around that, and still very cost effective, especially when you compare it to a concrete footing. So here's another view of it, again, kind of through that backfill and assembly process with the ribs. Again, you can see those ribs across the top. Okay, so I'm going to just go ahead and start this video. So this is a project near Mud Lake, or in Mud Lake, I should say. It's called Owsley Canal, and ITD was looking for essentially a replacement to this bridge, either extending on or replacing in kind. And what they eventually decided to do was build a plate structure, in this case a pipe arch shape, underneath the existing bridge. And so while this plate was being assembled and backfilled, you can see the bridge itself was still intact and being used. And so they went a little bit wider here, and eventually what you'll see is once they get the end wall here and the apron built, this is all cast in place concrete, and it's done in the winter time, so it's somewhat of a slow process. But then they grade that out to where there's a bypass road that will eventually be built here, so that as they tear out the old bridge, they can still get vehicles across. So very minimal disruption to traffic. It's not a real busy area anyways, but at least they had the ability to route traffic around this bridge while it was being built. There's the new road, bypass road, and then you'll see that bridge here disappear. Right, there it goes. So yeah, and then they'll eventually grade that out and move traffic back onto that road, and everything's you know, as it was before, other than the bridges is different. It's a different bridge. So we like to show that just because of the you know, the ease at which you can replace an existing bridge. And it was, I think, about half the cost. It was scheduled to be a $1.5 million bridge replacement, and with the plate structure, it ended up being a little less than $800,000 for that.
What would the original bridge material have been if it had been 1.5 million, Chad?
Probably I believe a concrete girder style bridge.
Okay.
Similar to what, yeah, just newer, upgraded. Okay, so then I wanted to finish off with essentially the capabilities of this structural plate material, that we can span pretty good spans. This is across I-80 in Wells, Nevada, or near Wells. This is a wildlife overpass, so traffic on I-80 is going through this structure, which is a 66-foot span, 26.5-foot tall arch, and then eventually it gets buried with end treatments, these panel walls. And you can see the fencing over the top of that. So that's all for wildlife to go over. And this is in the Pequot Mountain Range. So mostly deer, I believe. And you've got essentially 3 lanes of traffic going through it there. So provides plenty of clearance, and it shows the capacity of the plate structures and utilized in a variety of applications. Any questions on that, or anything else with our structural plates? This is really the last part of the presentation on structural plates. So
I don't have any questions coming into chat, so we can move on. If you guys have any, just go ahead and send them in, and we can always jump back to it.
Yeah, okay. Well, let me share a few things. You know, I talked about buried bridges, and so our plate, I'm not sharing anything on the precast side of things, mainly because what I shared with plate structures is geared towards small municipalities and very, very cost-effective product type. There are occasions where a truss bridge might be utilized in municipalities. There's certainly trail systems, or getting over canals, or separating traffic and from pedestrian vehicular traffic. And so wanted to share a few projects where we've done these truss bridges. And this one in particular is in Idaho Falls. It's at the
I recognize that bridge.
yeah, it's at the Hilton True hotel that was built. Probably nobody's staying at right now, or very few. But this just is a canal crossing. It's an arch, what we call a keystone style, and there's lighting. You don't see it in there, but there is lighting that is built into the vertical studs there. So that was one that we did there in Idaho Falls. This one is in Boise area along the Whitewater Park, as I recall. That's the name of the Whitewater Park, I believe. Yeah. And there's a trail system that essentially follows the Boise River, and there was 2 of these pedestrian bridges that were installed. This is a very basic, the connector style, very inexpensive, most common bridge type that we use, or that we see used.
So Chad, who, this is more me from a local level, who manages that? Because that's going over the river. So is that the city that manages it because it connects to our green belt? Who's responsible for those pedestrian bridges?
I would assume Boise, maybe the Boise Parks and Rec Department, or just the city itself. Yeah, I think so.
That would make sense, because they're connecting, that one in particular is connecting 2 parks across the river.
Yeah, I would assume they manage it.
Okay.
And then this one is actually across the Boise River. This is in Garden City. And because of the span, we get to what we call a box truss or a through truss. And so you can see that essentially that square shape of the bridge to accommodate roughly about a 200-foot span. And I don't remember the width, and most trails were about 12 feet wide, so I assume that bridge was probably 12 feet wide. All right, any questions on truss bridges?
Let me see.
And just a few little snippets of these steel truss bridges and their applications.
So I do have a question that came in. Is there a limit on, let me see if I'm reading this right. Is there a limit on how short and how long these can be made, or are they custom made?
The steel truss bridges?
Yeah,
there's the limitations. I mean, I think effectively we start at about 20-foot spans as a minimum. And then we can span, I've seen a clear span of 315 feet. So that's a single clear span with abutments on either side. That's a very specialized bridge design. We call it a tight arch. It's a very high profile, very expensive bridge, I might add, but it is possible to clear span, 300 foot with one bridge. Other times I've seen multiple spans used, to get 600 feet of span, but do it in, multiple bridge pieces. So I guess there's all kinds of options there, but yeah, I'd say from 20 to about 300 is the range.
Is this a situation where they would reach out to us with a project and then have us just kind of look at it and give options out of the different bridges and trusses and say, here's what we would recommend based on your project?
Yeah, I mean, sometimes there's folks that are involved have an idea of what they want the bridge to look like.
Yeah, I guess that's visual.
If there's a particular span, that span might dictate what options are available as well. So those are, yeah, there's a couple things that play into that, but for the most part, the easiest thing is we've got a booklet that shows all the truss bridge options, and then we just share that, and whoever's looking at it can decide what they think is the most appropriate.
Okay. For
starters, and then once we get involved, we can provide some guidelines as well.
I don't have any more questions coming into the box.
You said a minimum bridge length was about 20 feet. Do they extend those in increments of 10 or 20 feet, or how does that work?
We have a standard bridge that's in increments of 10 feet, but you can go whatever size. Yeah.
Okay.
So we'd call that a custom, but if it's in 10-foot increments, it's really an off-the-shelf design. So yeah, that's a good question. Okay, so that's truss. Let me just go back a little bit in terms of, the corrugated steel, galvanized steel. We do make a product called bridge plank, which is utilized commonly for replacing or resurfacing an existing bridge. So if you've got a bridge where the the underside is fine, this superstructure of it is fine, we can put a new deck on it with this bridge plank. Bridge plank comes in essentially 3 different profiles. Again, we talked about that 6 by 2. The bridge plank comes in that same profile. This is what we're seeing here. On the right, there are a couple of charts, and on the bottom is really what I want to highlight there. There are 3 different gauges, 12, 10, and 7 in this particular profile, the 6 by 2. And how we're able to come up with the gauge is by 2 pieces of information. One is the span, the net span between girders or beams. So we need to know what that space is between beams, and then the live load. So HS15, HS20, 25. And if the net span is, say it's 20 feet and 25 HS25 live load, then a 12 gauge material would work. If we need to bump that down to a 24-foot span between beams, then we're looking at a 7 gauge. So just gives you an idea of how quick and easy it is to reference what gauge would be required for that. So I won't belabor that same point, but we do have different profiles in 9x3, which is probably the least efficient because it only comes in 9-inch wide pieces. Go back, the 12 or the 6x2 comes in essentially a 24-inch wide piece. So you get 2 feet every time you lay it down versus 9 inches for this. And then the other one is a 12x4.25, which is again a single piece of 12 inches wide. So it's still a little bit more efficient, but the same properties apply here. The gauge is determined by the span and the live load. So that is bridge plank, again, commonly used to resurface existing bridges. And that material is made in Winchester, Kentucky, as is the plate structures. The steel truss bridges we build in either Colorado or Minnesota. Okay, so just a few things just to wrap up, some take-home points here. Really, the idea behind all this is these are essentially pre-engineered systems. We have a design booklet that is available that you can reference just about every type of structure plate structure that we manufacture and design. There are some custom builds that we do that are not in this booklet, but when they're pre-engineered, they save time and money, obviously. You can improve the lifespan, that durability by either increasing the gauge as one option. We didn't really talk about that. Changing the material to aluminum, which we did talk about. You can also cover it with a membrane or pave the invert if the inside is susceptible to abrasion and corrosion. One benefit is if you can go with a taller structure, if it is a deep fill, you can reduce that amount of fill and utilize maybe a lighter gauge thickness and a reduced footing size. So sometimes those taller structures are more beneficial for a deep fill situation. The full inverts, obviously I mentioned that, can be a lot less expensive because you're eliminating footings. The concrete footings can get fairly expensive, especially if they're precast. And then just reiterating that one of the most important things that we look for early on in the project is a geotechnical report to help us determine what the plate material type should be. It also helps us with designing the footings and determining if the backfill or if that material could be suitable backfill material. So that's really pretty much it. I think we've run over just a couple of minutes on our time that we had slotted, but that's the presentation. So
I have no more questions in chat, so I think we're good to wrap up. You guys are going to, well, thank you for joining, first of all. You guys will be getting a follow-up email tomorrow that will have a recording in case there's anything you want to go back to in Chad's presentation, as well as it'll have Kelly and Chad's contact details. So if you guys need to reach out to them, it'll be coming from me. So if you need to reach out from me, you'll already have my email address, but I'm definitely no expert on bridges, so these guys will help you out.
Well, thanks for having me.
Yeah.
Thanks, Chad. Thanks, everybody.
Happy to help.
We'll let you guys know next week we'll be doing a hour-long engineer in-depth bridge webinar. It'll be focusing on very technical stuff. I don't know if we have any engineers on the call right now, but we will be sending information out about that.
Great,
All right.
thank you.